Good morning, teacher and dear friend. It's my honor to join you for the workshop. My topic this morning is about artifact of ultrasonography. As you can see here in the picture, there should be some artifact. For example, here an image on the surface of the lake is not real, so it should be artifact. But the others here are real structures, or for example, the swan. I'm Yihong Chou from Taiwan, and now serving as chair professor at Yuanping University, Taiwan. Why there are artifacts during sonographic study? Some could be resulting from improper equipment operation, improper equipment setting, improper scanning technique, and some are related to ultrasonic factors. I would like to emphasize the ultrasonic factor because it is related to interaction of sound wave with the transducer or tissue in human body, and sometimes cannot avoid. Almost all ultrasound equipment have a certain handling assumptions. For example, all tissue has the same acoustic velocity. Ultrasound energy travels in straight line in tissue. Distance proportional to round-trip travel time. Echoes originate from points along the main beam axis. Echo's intensity is related directly to the reflection or scattering properties of object, and all detected targets are on the central ray of the transducer beam pattern. So if there is any assumption of violated, an artifact occurs. Starting from the multipath artifact, so-called multipath is a kind of multiple reflections. For example, Refraction Artifact, comet-tail, rain-down, mirror image, and mirage artifacts are related to multipath. A typical example is just like this. When you scan the lung, you can see a lot of refraction artifact. This kind of artifact is a kind of reflections one by one, and the subsequent refractors is weaker than the prior ones. It's because the reflection between the transducer and the strong refractor here, for example, this lung, air. So air is a real one, and the others are refraction artifact. Why the air is so strong in reflection? Here you can see the impedance of air is about 0.0004. That means air is very soft, very compressible, but bone is very hard, and soft tissue in between. And talking about the refraction coefficient is related to the difference between two refractors. For example, the muscle 1.6 and the air 0.0004, so the difference is huge. Therefore, the Zo2 minus Zo1 divided by Zo2 plus Zo1 in this example will be about 100%, almost 1, so 100% refracted. That's why air, whenever you encounter air, almost all are refracted, all the energies. So here is a typical example by schematic representation. There's a real lung because it's reflected back to the transducer, but the transducer is also a strong refractor, so bound back again and again, so the second, the third, the fourth, and each subsequent refractions is weaker than the prior one. So here you can see reaberration, and here a relatively complicated reaberration is so-called dirty shadows, because it makes a lot of different refractors here. There's a corresponding CT pattern. I magnify this for you to see the wall of the stomach and the air and the reaberration. Reaberration is not only noted at lung sonography or small bowel study, and here is an example of Stockholm renal stone, also causes this kind of reaberration. Not commonly seen, but occasionally. And reaberration here is not a reaberration, it's a kind of mirror image. Here you can see the viscera lung, viscera pleura or lung, and here is the muscle, that's a diaphragmatic muscular bundles, and here you can see in between liver and the diaphragm there's a liver capsule plus parietal peritoneum, so the muscle diaphragm here reflected to here, so this is a mirror image, and for this there's a real, and this is mirror image of the interface between muscle and the liver. So this diaphragmatic presentation, and here scanning the liver right lobe, you can see a hyperechoic structure. It should be most likely hemangioma, but here you can see another one. Actually, this is not a real one. There's a reflection from this real structure, so there's a pseudo hemangioma above the hyperrefraction. Hyperrefractor here, that's the viscera pleura or lung. Just like this. A is a real one, A prime here, a pseudo hemangioma. And sometimes cystic structure can also reflected above the diaphragm. Here I can see something above the liver and above the diaphragm, just like a cystic structure. Should be real. I do it again, I can see this, but sometimes I cannot see. So here you can see the real structure in the inside the liver. That's inferior vena cava and prominent hepatic vein. Is that artifact? Now I can see both sides. One below diaphragm, one above diaphragm. This is real hepatic vein and IVC. This is refracted structures from below the diaphragm. So this is a mirage artifact, real image. This is a mirror image. True, false, false, true. Sometimes can be so real, the artifact. Here you can see completely reflected above the diaphragm. So false and real. Mirror image artifact. Now about ring down. A very important study by Cooperberg group in 1985 to demonstrate it the gas bubbles inside a water bag can cause this kind of air bubble artifact or ring down artifact. The schematic representation here to show you the air bubble and in between the fluid trapped inside. So when the sunbeam, the main ultrasound beam, transmitted to the fluid and reflected in between the gas bubble, then a continuous source of sound energy go back to the transducer. So you can see this kind of parallel refractions. Again, there's a mid-abdomen and lower abdomen by doing a transvaginal ultrasound because of a small bowel gas. And in the upper abdomen, quite often you can see this kind of a reversion artifact, a specific reversion artifact, ring down artifact, arising from the gas bubbles in the stomach. How about this? It's just like cometail, right? So this is a kind of a cometail artifact caused by tiny stones or crystals in the hydronephrotic kidney. And here an IUD inside the uterine cavity. There's a cometail artifact arising from the metallic object. And not uncommonly, you can see the artifact from the cholesterol crystals, tiny calcifications, or small stones. Refraction artifact. Just like light, sound can also have this kind of artifact. It is it should follow the Snell's law related to velocity, not acoustic impedance. So here you can see two different medium. The first medium got velocity v1, and the second medium got velocity v2. If v2 is greater than v1, then the sunbeam hit the surface of second medium, the sunbeam will be deviated, and then deviated again because hit the v1 through v2 hit v1. So you can see the sound go like this, but because the machine just think the reflector should be a straight line, a sunbeam should penetrating through this structure by a straight line, so this structure will be placed in this area. So B is a force displaced. Okay, now about reflection and reflection combined together to cause a critical angle artifact. Here reflection, here refraction, and then you can see two critical angle artifact or lateral shades on the margin of the cystic structure. In this example, that's gallbladder. Okay, and not always on the margin of the cystic structures, but sometimes from the curved or oblique reflectors. Here is an example from the Farcival ligament or round ligament. Also a kind of a reflection artifact. Reflection artifact from a hepatic cyst, but here is that a kind of a critical angle artifact, but here you can see a little bit dirty, so not quite typical. Actually, this is caused by air bubbles on the gallbladder wall. So this is so-called emphysematic cholecystitis, air bubble trapping on the gallbladder wall. And here there's a spleen, there's a left kidney, but why the left kidney is crooked like this? Because of a refraction from the different velocity. There's a spleen faster, fat slower, so the lower part of the kidney is depressed distally. So it's a kind of refraction artifact plus speed error displacement. And here, two Foley catheter bubble, for catheter balloon, just because of the rectus muscle here serving as lens, and therefore refraction occur, and one balloon look like two balloons. And in this situation, you can move the transducer lateral to the midline, then you can see only one single balloon. Side lobe artifact is because of the energy from side lobe. The main lobe is sunbeam we used for sonography study, but the side lobe signals can be also detected. So that's a main lobe detected hyperrefractive structure, but side lobe also sees this and register the signals on the side of the hyperrefractive structures. So side lobe here. Now another commonly seen side lobe is on the braided base. Here you can see two side lobes along the hyperrefractor. And now slice thickening artifact. It's just similar to partial volume artifact on CT because the sunbeam got 3 dimensions. One for axial resolution, one for lateral resolution, and here is the slice thickness. So it's so-called elevation resolution. Because the elevation or slice thickness is too thick, then it will detect some signals on the peripheral region, not in the main beam side. So it can display as weak internal echoes, just like here in the gallbladder. So slice thickening artifact. Everybody knows this because that's called typical acoustic shadows from gallstone. But how about this? There's a Niger hyperechoic with acoustic shadows. Could be intrahepatic stone, but actually not. It's fat. So lipoma can cause this kind of acoustic shadows because of the strong attenuator. Or here another strong attenuator that's fatty tumor, actually liposarcoma, retroperitoneum. So acoustic shadows or strong attenuation. And attenuation can be also encountered during sonography study for fatty liver, particularly if you are using high frequency transducer, the distal portion is strongly attenuated. So acoustic shadows can be clean like gallstone, can be dirty like air. There's a kind of complicated reverberation artifact, and also from the critical angle artifact or refraction artifact. And if the structure here between the inside the liver parenchyma is a weak attenuator, then there should be distal enhancement or increased through transmission here. Again, enhancement, critical angle artifact in the typical renal hepatic cyst or gallbladder So in conclusion, artifacts are commonplace in ultrasound. Often these errors in image display are unavoidable and occur secondary to intrinsic physical properties of the ultrasound beam and its echoes. Artifacts are important because they may be clues to tissue composition and may aid in diagnosis. There are common examples. You know the answer. There's a ring down artifact. How about this? Comitail, no doubt. Comitail. How about this? Double Foley catheter balloon. So there's a refraction artifact or lens artifact, sometimes called phantom or ghost artifact. And here you can see something wrong with the liver. It's bright here, it's dark here. Is the hyperecho area focal pathology? No, that's because of fluid ascites enhanced the liver here. How about diaphragm here? Seems to be interrupted. Actually, that's caused by liver. Different velocity between liver and ascites. So the diaphragm seems to be interrupted. And so you know the nature is a combine of speed, error, displacement, and refraction. So thank you very much for your kind attention. Any questions?